Hello everyone, welcome to today's video of numerical integration on the topic of general quadrature formula. In this session, we will learn about the integration, numerical integration and the general quadrature formula. This formula will be useful to find other numerical integration methods which we will cover in the upcoming lectures. Let's get started. Let's quickly refresh our memory about integration. It helps us understand the cumulative effect of a function over a given interval. Think of it as adding up the tiny slices of curve to get the total area. So if we need to find the area under this curve, we will take area above x-axis as positive and below the x-axis as negative. Note that here we are integrating with respect to x. As we are integrating the function fx, so we will write the function fx along with the integral sign, and as we are integrating with respect to x, so we will write dx. Now let's understand the types of integration. Integration is of two types, definite integration and indefinite integration. Definite integration is used to calculate the exact numerical value of the integral of a function over a specified interval. It provides a single numerical value as the result, and this numerical value represents the accumulated area under the curve of the given function with the given interval. The integral sign is accompanied by specific limits of integration denoting the starting and the ending point of the interval. So this integral of fx dx from the limits a to b represents the definite integral of the function fx from point a to point b on x-axis. Second type of integration is indefinite integral. This is used to find the general antiderivative of the given function. So here fx dx represents the indefinite integral of the function fx with respect to x. This yields to the family of functions fx plus c, where fx is the antiderivative of fx and c is the constant of integration. Now let's understand numerical integration. It is also known as the numerical quadrature. It is a method used to approximate the definite integrals of the function when the antiderivative cannot be found analytically. Note here that one-dimensional integrals are also known as numerical quadrature, and more than one-dimensional integrals are known as numerical cubatures. Let's now understand that why numerical integration is necessary. So, in many cases, finding the exact solution to a given definite integral analytically can be challenging or even impossible. This is especially true for the functions that are complex, irregular, or have no closed form expression. Numerical integration provides a way to find the approximate value of the integral by dividing the interval into smaller subintervals and summing up the contributions from each of these subintervals. The basic idea behind the numerical integration is to approximate the area under a curve by dividing the interval into small segments and approximating each segment area using the simple geometric shapes like rectangles, trapezoids, etc. By summing up the areas of these geometric shapes, we can get an approximation of the total area under the curve, which corresponds to the value of integral. Let's now find a general formula to understand this quadrature process. Let there be a curve y is equal to fx. Let's draw this curve and divide it into some equidistant points. Here we have taken various points y0, y1, y2 up to yn which are equidistant lying on the curve y. So now we have to find a definite integral fx with respect to x-axis from the limits x0 up to x0 plus nh, because the starting point here is x0 and the last limit point is x0 plus nh. Let's now use the Newton forward interpolation method, which we have already discussed in the previous video. If you haven't seen that video, then I will provide its link in the description and you can watch it. Here u is equal to x minus x0 divided by h. If we rearrange it, then we will get x is equal to x0 plus hu. Differentiating on both sides, we will get dx is equal to h times du. Now we will use this equation to convert the limits of our definite integral into another form. For the lower limit, we have x is equal to x0. So putting the value of x is equal to x0, we will get u is equal to 0. Similarly, for the upper limit, x is equal to x0 plus nh. So here we can solve this equation as u is equal to n for the upper limit. So now we have to integrate from the lower limit u is equal to 0 to the upper limit u is equal to n. Originally we have to integrate y with respect to x and the limits were x0 to x0 plus nh. So after conversion also we have to integrate y. We have already calculated that dx is equal to h times of du. So in place of this dx we will write h times du and the limits are now 0 to n. So the lower limit being 0 and the upper limit being n. As this h is constant, it will be taken outside and we will expand this y using the Newton forward interpolation method, and we will now integrate with respect to u. Let's use the Newton forward formula to calculate this integral. We can expand y as y0 plus u into delta y0 plus u into u minus 1 by 2 factorial delta square y0 and so on. And you can see that I have replaced dx by h du. As this h is constant, so you can take it common and we have to integrate rest of the terms with respect to u. Integrating y0, we will get u y0. Integrating u delta y0, we will get u square by 2 delta y0. Now integrating u into u minus 1, we will get u cube by 3 minus u square by 2 delta square y0 divided by 2 factorial, and integrating in a similar manner we will get all these terms. So now the limits of the integration are 0 to n. So now we have to expand these terms which we have got after integration by using the limits 0 to n. Here the lower limit is 0 and the upper limit is n. So we will get, so this formula is known as the Newton-Cotes general quadrature formula. This is known as the Newton-Cotes general quadrature formula. This formula is very useful in finding various other methods of numerical integration. For various values of n in the Newton-Cotes general quadrature formula, we'll get different types of numerical integration methods. We will learn about these methods in the next videos, and we will also solve the relevant examples there. So stay tuned for the upcoming videos. If you have any doubts, then you may ask in the comment section. Thanks for watching. Don't forget to like, subscribe and hit that bell icon for more such videos. Have a nice day.